Hello everyone. Let's keep talking about electricity and magnetism, non-calc treatment. Let's talk about the Serway book. Again, the Serway and Buell book, 11th edition, abbreviated as the Serway book in our colloquial discussion of the matter. The Serway book, practice physics, we're going to do some of that. Chapter 18 from the Serway book. Let's do a little bit of that. From chapter 18, problems found on these pages. These are the problems I'm going to try to do. I've already written the basic outline of the first two of these problems. I mean, we got the problems, problems 7, 11, 13, 15, 23, 30, 31, 39, 47, 59. So let's have a look here. That is 10 problems. So let's see what we can do. I've got the first two kind of written down in an outline format. Let me do problem 7. Hopefully there's enough room here. I'll eventually get rid of this, and then we'll just jump over to problem number 11 and then just take it from there and see how we can get through this. Again, from the Serway book, chapter 18. Again, chapter 18 means topic 18. The way the Serway book writes it, calls it, it's topic 18. I'm calling it chapter 18. Same thing. Problem number 7 from topic 18 says, find the equivalent resistance between points A and B in the figure. Calculate the current in each resistor if a potential difference of 34.0 volts is applied between points A and B. So there's a potential difference between points A and B of 34 volts, and they want you to calculate the current in each resistor if a potential difference of 34 volts is indeed applied between the two. Find also the equivalent resistance between all of the points given all this right here. So 34, it's going to go from here or from there, but let's say it's going to go here, high potential to low potential. Potential difference between them, or let's say high potential, low potential. Let's just say the positively charged current. Now again, the charges typically are negative, but the convention is you pretend that you're dealing with positive charges, or how would positive charges actually move? It's just a question of direction. For all intents and purposes otherwise, it's not really an issue. It's not really a problem. You can visualize it quite well. And again, the usual technique is to say for positive charges. Okay, so potential difference of 34 volts between the two of these. Find the equivalent resistance, and from there, you can find the current that's going to go through in totality. From there, I'll tell you what, because, just from the structure of it, we can say a few things here. When I find the equivalent resistance, the total current that goes through here, the total current is going to go through this guy and is also going to go through this guy, but it's going to get split up right here. And the one with less resistance, it's going to have more current going through it. How much more current? Proportionately speaking, it's inversely proportional to the resistance. So if this has X amount of current going through it, this right here is going to have 10 divided by 7 times X amount of current. If this is X amount of current going through it, this right here would be 10 over 7 times X. There's a lot of other ways to do it, but that's something of interest. I mean, kind of to look at. I think it goes pretty good for us if we look at it in that manner. So, let's see what we can say, guys. We'll cross all the bridges as we have to cross them, guys. Let's just get there first. What we have here is these two are in parallel, so let's get an equivalent resistance here, and then let's add the resistances after we get an equivalent resistance right here. So let's look at this. Let's get an equivalent resistance. The equivalent resistance right there is going to be 1 over R. It's going to be associated with the mathematics of 1 over R. 1 over R equals 1 over R1 plus 1 over R2. So 1 over R is going to equal 1 over R1 plus 1 over R2, and now just do the mathematics to get what you have to get. Looking at this, special one here of 10 over 10, would give you 10 over 70. Special one here of 7 over 7 would give you 7 over 70. One over r is 1 over r. Let's add these two together. They're equal. Their reciprocals are equal. That's going to be equal to, if two things are equal, their reciprocals are equal. That's going to be 4 and 2/17. That's 4 and 2/17. Now you've made this arrangement that's in parallel of resistors, this arrangement of resistors that are in parallel, you've made them into an equivalent resistor, one equivalent resistor that's in series with these two. So 4 plus 4 and 2/17 plus 9 plus 9 is the end of the story, you guys. So we got 4. So you're just going to take the 4 ohm, the equivalent of those two that were in parallel, which is this, and the 9 ohm. You add these together, should be the equivalent resistance. Let's talk about it. Again, guys, these will scroll at the end, and in addition to other problems, they're also going to scroll at the end. Yeah, that's fine. That'll work. Depending on how they're asking you to answer the question, I guess, right? It's always a question of how they want you to answer the question. Our equivalent is 17 and 2/17 ohms. That right there, guys, that right there, that's the answer. That's fine, that's the answer. So is this. I mean, for our purposes, this is a more exact answer, actually. But if they want it to 2 decimal places, there you go. That'd be the answer regarding that. So that's A. Okay, well, if that's the case, we've said a few things. I mean, so let's see what we can do here, guys. Let me let's take some of this stuff off of here. So there's your equivalent resistance, the 17.17. I'm almost at some level. I'm almost tempted to keep this because there's going to be some division in here that's going to make this pretty manageable. But really neither here nor there, guys. I mean, it's going to be the answer is going to be the answer. If we know what we're doing, the degree of accuracy to which we are doing something is something that is potentially negotiable. I mean, somebody could say, okay, well, give me this accuracy to 1 decimal place, to 2 decimal places, to 3 decimal places, depending upon what they're asking. That's how something can be asked. So, I mean, we said a bunch of things. We came up with a good answer. Tell you what, we know that V equals IR, or delta V equals IR. Here's that delta V again, right? V or delta V, no matter what, depending on what we want to do, right? V equals IR. I equals delta V over R, or V over R, the way I'm usually writing this stuff out. Let's just see what all the current is in total. They wanted the equivalent resistance. Calculate the current in each resistor. I'll tell you what. Let's make this a lot easier than you might think. they're telling us V is 34. And this right here is 17 and 2/7, which is interesting. I could actually put 17.12 right here. That's probably the better way to do it. Or you can put this guy in here just to kind of, you can say, well, how will this work? Well, 17 times 17 is its own dynamic. What we're talking about, right, this is 289. You multiply 17 times 17, that's 289, plus 2, that's 291. 291 over 17, and there's stuff you could do. You're probably inviting more of a hassle for yourself than you actually need. Let's leave it like this. Take it to any degree of accuracy you wish with the decimal approximation, and let's just see where this is going to go. That I right, and it's almost 2, which makes sense. This is almost 17. 17 goes into 34 twice. 17.12 will not go into 34 quite as much as twice, but it'll come close to going in twice. So it comes in what? So what we have here is the current from start to finish is this. What does that mean? Well, that means that right here, for this guy, let's call him I1, that's 1.986 amps. And again, in my notes, I probably showed it a little differently, guys, but that, like I said, that's neither here nor there. Get the right answer at the end of the day there. That's what's going through this guy. That's also what's going through this guy. That's the 4. So in other words, I sub 4, I sub 1 or I sub 4. We call them different things. Let's call this guy I sub 9. That's the 4 ohm resistor, 9 ohm resistor. That's this guy. That's this guy. True. These guys in totality also have a total of 1.986 amps going through there. True. But yeah, it's separated. It's not separated equally. If they both had the same exact resistance, this thing would be cut in half. The roughly 2 right there would be cut in half. Each one would have about 1. Each one, if they would be cut right in half, if that was the case. But it's not. This is going to have an amount of current. I've seen different ways. We can look at this at 2 ways. I showed this in a number of ways too. I'm just going to I'm going to show you the first way. I just think it's easier, but I got them both here. It's all in the notes, you guys. So when you look at it, you look at it. This is less resistance than that, so this has more current. This is current X. So this has current X right here, guys. This has got current X. This has got 7 over 10 times X. Or you could alter it and say this guy's got X and this got 10 over 7 times X. It doesn't matter which way you go here. If you call this guy on the bottom X, it's the low current. How do you get higher than X? Multiply by 10 over X. If you call the high one X, how do you get low from the X? 7 over 10. It's the 7 and the 10 coming into play as fractions, you guys. The low resistance resistor has the higher current, period. And in a mathematical sense, we can see that pretty straight. So what are we talking about here? What we're talking about should be pretty straightforward in that regard. So what you're looking at you've got the high current, which is X. We'll call it 1 over X. The low current, which is 7 over 10 times X. Equals almost 2. The rest is algebra, guys. The rest is pretty basic algebra at that point. 7 over 10 is 0.7. 1 plus 0.7 is 1.7. 1x plus 0.7x is 1.7x. Could tell you the big one, guys. X is going to be that guy, which is going to be so. Let's see. We got the 1.7. X is associated. X is equal to the current associated with the 7 ohm resistor. It's the big one, right? It's the big amount. It's the big amount of current when we see that. So what you say here, it's 1.187 amps. The 7/10 X is equal to the small one. Sure. Well, don't they all got a total? Don't they all got to meet up and be equal to, be equal to this amount? This 1.986? Yeah, they do. So what would you have to add to 1.9? What would you have to add onto this to get 1.986? You'd have to add a 0.8. So let's see it. A 0.8, a 1, and a 6. 0.186. Yeah, we rounded it to 0.2. I'm sorry. We rounded it to 0.82 rather. That's this guy. That's the other one. It's looking all right. Is that true? Yeah, 1.17 plus 0.816 is 1.986. Yeah, so they round that to 0.82, and that looks good. Okay, so that's 7, and let's go to 11, you guys. So basically, guys, even here, we could have done, you could have taken the 1.87 and gone 7/10 times 1.87, and it'll get you that answer, or at least very much in the ballpark of that answer, depending on how things have been rounded off and stuff like that. It's not a big deal. The big thing is here, guys, is that 0.816 amps is 7/10 of 1.17 amps. If you took 0.186 amps and divided it by 1.17 amps, you get 7 over 10 as a ratio. You should get 0.7 or very close to that. Okay, that's some of what's being said right there, you guys. Let's go to 11. All right, for number 11, consider the circuit shown, and they got A and B here. Find A, the potential difference between points A and B B, the current in the 20 ohm resistor. So they want you to find the potential difference between points A and B and the current in the 20 ohm resistor. Well, I'll tell you what, a lot of times when you're doing problems like this, you guys, you're better off answering a lot of questions. So it's forgive me there, guys, it's 25 volts potential difference. .25-volt resistance. What's going on here? Can I find the potential difference between A and B? Can we find out what's happening here? Well, the current for our purposes, the current in our schematics, guys, is going to flow from here. The current, the positively charged current, is going to flow from here all the way, hit everything here, and then come back here. I'd like to find the potential difference between the two. Well, whoever's got the bigger potential difference, and then I'll just say this has got potential difference Y, and this has got potential difference X, and Y minus X would be the potential difference. So let's see what we can say here, or say which one has a bigger potential difference than the other. So when we look at something like this, guys, I guess my idea of looking at it is the way this is set up right here. There's this guy, you're tempted to look at it and say that the 10 ohm resistor right here is in parallel with these guys. Well, not really, because it's associated with the battery here, and so at the end of the day, all of the current that comes together is going to come together right over here. All the current that flows is going to come together over here, and it's also going to pass through the 10 ohm resistor. That's not the case with this 10 ohm resistor, nor with this 5 ohm resistor, nor with this resistor, nor with that resistor. Here there's a lot of separation going on. Whatever separation takes place here, they're in series. They're going to have the same current going through them, whatever it is. This is going to have some other current going through it, and this is going to have yet some other current. You know, they all could have the same amount of current going through them, but you'd have to add them together at the end anyway. Let's say all together they have current, an amount of current X going through them. This is amount of current Y going through it. This is amount of current Z going through it. You add them together at the end, and X, Y, Z is what's going to go through here. X plus Y plus Z is what's going to go through here. So that's not parallel to these, but these are parallel. These are in series. Add them up and get kind of, let's try to get, let's know a lot before we say anything. Well, if I add these two together right now, because they're in series, 5 and 20 is 25, and then you got a situation where you got a 25 ohm resistor, the equivalent of a 25 ohm resistor, a 5 ohm resistor, and a 10 ohm resistor. They're all parallel to each other. They're all parallel to one another, guys. And what we have is Those right there are going to equal the equivalent. We didn't put this guy in here. I already told you we didn't put that guy in there. There's a lot of ways you can do this. Here's a 10, here's a 5, here's a 25. I tell you what. Why don't you go 2 over 2, multiply 1 over 25 by a special 1 called 2 over 2. Multiply this guy by a special 1 called 10 over 10. Multiply this guy by a special 1 called 5 over 5. Add them together. 5 and 10 and 2 is 17. The R of all that, the equivalent resistance of all that is going to be, flip them both upside down. That's almost just flat out 3. That's 2 and 16/17. And I'm going to put that in series. When I find that, the equivalent resistance, you can then put it in series with the 10. So the real R equivalent is going to be the R, which is 2 and 16/17 and 10. So let's see what we got here. Let's see how they actually went about it. Right, so we got the equivalent resistance, and then we just said I in totality correct. I mean, it was basically just the V over the REQ. As we have in the notes there. The I in totality is going to be 1.932 amps. So there's a lot you can do here, guys. You can say a lot here. I'll tell you what, the potential difference, the tendency for this thing to want to bring current from here all the way to here is every bit as much as the 25 volts minus what gets lost here when the totality of the current goes through there. I'll just say it in plain English, guys. I mean, the way they have this is they're saying that delta V, the potential difference between the two, is the same as 25, but ain't quite as strong as that. It's the current minus R, is the current times R10, the R of the 10. So what are we talking about? Is 25 minus 1.932 times 10. .68 is the potential difference regarding that. Now they're simply just saying, guys, find the current in the 20 ohm resistor. The current in the 20 ohm resistor is the same current that's going to pass through the 5 ohm resistor. They both have the same current going through them. Well, how much is that? Well, the total current in totality, so to speak, is what's going through here, and then it's going to break up all over the place. The totality of the current, the totality of all the current, the equivalent current, let's say if you just have one resistor, you got the equivalent resistor, the totality of the current is 1.932 amps. 1.932 amps. Right. Now that 1.932 amps is going to get broken up between a total of 25 ohms, 5 ohms, and 10 ohms. And, you can answer more questions than you're even asked at that point. You got that right there. What do you think? Well, the 1.932 amps is everything. We've already accounted for it. This guy was in series. Okay. Well, we know the 1.932 amps is going to go through here, and it's also going to leave through there. It's going to break up here. Here's 10 ohms, here's 5 ohms, here's 25 ohms. Wait a minute. Didn't we say the less resistance, the more current is going to happen, given the set amount of current that's eventually going to go through all of this in aggregate? All of the current, links up again, and it becomes the total current. 1.932. So what we have here is, when you're looking at something like this, 1.932 is the total. 1.932 amps is the total. It's going to break up. Here's 25, here's 5, here's 10. What's going on? Well, just kind of take a little bit of a shot at this. Here's a total of 25. Here's a total of 5. Here's 10, here's 5, here's 5. 10, 5, so forgive me. Here's 10, 5, and 25. This one's got the most current. This one's got, so we can work from the least. We can do a whole lot of stuff here to do this. Let's work from the least resistance has the most current. Let's say the amount of current here is X. This one's 25 times more resistance. I'm sorry, this is 25. How many times more resistance is it? What's 25 divided by 5? 5 times more resistance. 5 times more resistance means 1/5 the current. 1/5 the current associated with this guy. This is the one with the real big amount of current. That's 1 times X for that. This is 1/5 X. This is double the size of 5, which means it's half the amount of current. There you go. This is not the only way to do this, but I think it's a very effective way to do it. So when you do this, half of what the resistor with the big current has, the big current is associated, the big current in this partition is associated with the small resistor. It's current X. The 10 ohm resistor has half the current X. The 5 ohm resistor has the most current because it has the least resistance. It's got double the current that the 10 ohm resistor has. 5 ohm resistor has double the current that 5 ohm resistor has double the current that the 10 ohm resistor has because it has half the resistance that this guy has. This has 1/5 the resistance of the 25 ohm resistor. So it's going to have 5 times more current than that one. In totality, that's going to be the total current. So what do we got? 1.932 amps. So we got 1/2 X plus 1X plus 1/5 X. $1.932 amps. Let's add them together. This is 0.2x, this is 0.5x, and this is 1x. 1x plus 0.5x is 1.5x, plus 0.2x is 1.7x. So what we have here is this. So what do we got? Why don't you divide by 1.7 on each side and see what happens? X is going to be this. Et cetera, et cetera. 1/2 X is going to be 1/2 of 1.932. Over 1.7. 1/5 X is going to be 1/5 of the top answer. This is half of the top answer. This is the top answer times 1. The top answer, half of the top answer, 1/5 of the top answer. So what was going through there? I mean, essentially, the current going through the 5 ohm resistor was 1.136 amps. The current going through the 5 ohm resistor is 1.136 amps. Half that amount of current is going through the 10 ohm resistor. And 1/5 of what was the max here is going through the 0.227 amp. I'm sorry, the 0.227 amps is going through the 20 ohm resistor. And that's what's going on there, guys. So that's 7 and 11. Let's go to 13. I'll set that up for you in 1 second. Okay, guys, welcome back. I just wanted to take a little break, write some new problems on the board. I thought it might be a little more time efficient for everyone. On occasion, that has to be done. Sometimes that's not very practical. Other times, it may be practical. So let's take a look. 13 and 15 are the next two problems I want to do, 13 and 15. Now what they're saying for 13 is, 13, the resistance between terminals A and B. The resistance between terminals A and B in the figure is 75 ohms in total. If the resistance labeled R have the same value, determine R. So in other words, what they're saying here is the resistance between these 2 points. If you're flowing a current this way, it comes all the way back, the resistance that it encounters in total is 75. What would R have to be? What would R have to be for that to be 75 in total? Now we said all of the current, the logic we said for one of these, for this one in particular, for this R in particular, all of the current's going to go through this one. Whereas for these other ones under consideration, these two are in series with one another. So you'll add them up, R plus 5. Here it's 40. No, so this is R plus 5. This is 40. This is 120. Let's find that equivalent resistance. Let's find that equivalent resistance, and from there, we can say a few things. So what we have is, there's a lot of ways we can say it. Let's just call it R sub 1 is the equivalent resistance for the guys that are in parallel. Well, these aren't in parallel, they're in series. Add them together, and then the totality of it is in parallel with this, is in parallel with that. Then the three items are in parallel with one another. Let's say 1 over R1 for the parallels is going to be 1 over capital R plus 5 Let me put the watch on the other hand, guys. It's kind of left-handed and it's moving all over the place when I'm trying to do this. So you got R plus 5, R plus 5 right here. You got 40, you got this. Okay. The 1 over R1 is this. This. Let me just go the same order, I guess. I'm going from the far right going to the left, I guess you could say. So this is 40. That's it. That's the deal. So we've got this guy right here. And that's where we are. I mean, that's where we are with the whole process here, guys. So, you know, how are you going to do this? Well, I know it's a little bit, it becomes a little bit of a mess, but let's go for it anyway, I guess you could say. There's a number of ways you can go, and I have it in my notes probably slightly, well, maybe exactly the same as this, or close to exactly the same as this. Let me see how I want to do this. I mean, what I would actually do is, if this is this guy, and the other R is in series, this would be equal to, so there's a whole bunch of ways you can go. I think I did it essentially the same thing in my notes, but let me try to maybe look at this. I can do what I did in my notes, and the notes are fine. There's nothing wrong with that. It's a lot of ways to go. There's no real easy way to look at it, except for get what this is, and you know, what is that? That's a good question. Well, let's get a common denominator. How about this times 40 times 120? I'll tell you what, the 40 goes into the 120, so just let's use the 120. This right here would be, do a special one of 120 over 120. Okay. It's going to have to be the same thing. 120 R plus R, 120 times the quantity R plus 5. What do you say you multiply by a special one called 3 over 3 and another special one called the quantity R plus 5 over the quantity R plus 5? It's basically, if you multiply this by, you know, 3, how many times does 40 go into here? 3 times the quantity R plus 5. So R plus 5 here. The 3 and the 120 cancel to give you a 40. The R plus 5 and the R plus 5 cancel to give you the 1 over 40. That'll work. This is not exactly the way I did it earlier, but that's fine too. Put the 120 R plus 5. It's close enough. Multiply by a special one called R plus 5 over R plus 5. So there it is. What's going on? There's a lot going on. Look at it. Let's add them together and see what happens here. You got 1 over R1. Add the tops. 1 times the quantity R plus 5. 3 times the quantity R plus 5. That's 4 times the quantity R plus 5. Over 120 times the quantity R plus 5. Okay, well, it's going a little bit of a roundabout way here to get to this, but okay, we're not bad. Tell you what I'm going to do. Can you take a 4 out of here? Take a 4 out of there, huh? Take a 4 out of there. Can you take a 4 out of here? Yeah. There's a plus here. You can't really, it's tempting to think you can do a lot more than what you're actually going to be able to do. Okay, maybe somewhat easier to look at, I guess. Not necessarily real easy to look at, but there it is. So you got this looking as it does. Get the reciprocal of both sides, and you got what the R1 is. Get the reciprocal of both sides, 1 over R1. Get the reciprocal of 1 over R1. Get the reciprocal of 30 plus the quantity R plus 5 over the quantity 30 times the quantity R plus 5. Stuff's easier done than said. You got that, and you got 30. Okay, it's quite a bit. So you got that, and I guess the total equivalent resistance, the big resistance, 75, total equivalent resistance, 75 ohms, I think that's what they were telling us, right? Is going to be the R, the 75 ohms, is going to be the R plus R1. R1 is all of these guys at the end of the day. The R1, let me say, it's going to be plus the R1, and the R1 do a lot of stuff here, guys, I guess you could say. This is 30 plus R plus 5, 35 plus R. Yeah, I guess so. A lot of ways you could go. I don't know, leave it like this, don't leave it like this. For right now, let's leave it. It'd be 35 plus R. Let's stay like this for now and see what we can say. What would R have to be to make that happen? Yeah, there sure is a whole lot you could say here, guys. There sure is a whole lot. You know, we're not going to have any negative number on the bottom here, so that's going to be okay. I'm debating with myself what direction I want to go with this. There's a lot of directions you can go, so that's a good thing. So, again, where do we want to go? I mean, what do we want to do? I mean, I'm tempted to do a bunch of stuff here. They're all going to go. You can say that basically argue a whole bunch of things here if you want. Let's do this. There's no short way to do this, I guess you could say. If you're going to talk about 30 plus the quantity R plus 5, 30 and 5 is 35. 35 plus R. 30 plus R plus 5 is 35 plus R. Or R plus 35. Why don't you multiply by R plus 35 on each side of the equation and see what happens? kind of the argument. It's pretty crazy. Multiply by the quantity r plus 35 on each side. Okay. Well, that's it. Solve this equation. There's going to be two solutions. One of them is probably going to be absurd. The other one has to be the answer. Let's see what we can say to actually do this, to actually get this thing to work. There's a lot here. Like I said, I'm kind of going off script, you guys. And sometimes that doesn't always end up too good, but let's see where it does go, actually. We are looking at a situation here. Let me just see what the situation is. This will be 75R plus 30 times this is going to be 2250. If I just take the 30 from the 35, just take 30. 30 times this is going to be 2250. 5 times this is 375. So 375 and 2250 is going to be 2625. Unfortunately, I don't have a calculator on me, guys. I'm pretty confident that'll be the answer on this. Let me just kind of look at it just to be sure. I just want to argue this with myself a little bit, if you don't mind. 3,000 minus that would be 26. Right. This should be it. This is right. Assuming the assumptions early on were right. If we have to hook around, we have to hook around and do it again, but hopefully not. So r squared. So r squared, 35r, 30r, plus 150. All right, it's a lot. I mean, there's a lot there. And this is it. I mean, we're working along these lines. Assuming, this is the right logic, folks, assuming we did not do anything careless with our, with the earlier work. But the actual process is definitely correct. Now, let's see where this thing goes. Let's see what we're doing for an answer here. Could sure do a lot. I mean, let's see exactly what we're going to do. I'm going to see exactly how I wrote it. It was a little different. So that's about right. No, it looks for some reason, that's 450, 475. Right, this is fine. Looks good, guys. It looks pretty good. It looks like somehow we made the right assumptions here. Let's talk. Get all of this over there. Get all of this over there. R squared subtract 75r on each side. Subtract 2625 on each side. Subtract 2625 on each side. Should have done something up here, but that's okay. Negative 40R and positive 30R. Absolutely. That's what you're solving, guys. It's got the quadratic formula written all over it. Use the quadratic formula to solve for that. The R becomes equivalent in significance to the x. Ax squared plus bx plus c. Ax squared plus bx plus c equals 0. Solve for x. X is equal to negative b plus or minus the square root of the quantity b squared minus 4ac. The entire thing that we just wrote divided by 2a. Everything that we just wrote divided by 2a. That's the quadratic formula. You apply the quadratic formula, and I do have it in the notes in some pretty good detail. I actually do have the application there. I literally did the quadratic formula, set it up. I ended up getting 55 ohms and negative 45 ohms. 55 ohms and negative 45 ohms. Negative 45 ohms is ridiculous. Has nothing to do with what we're doing. Negative 45 ohms is ridiculous. Negative 45 ohms is ridiculous, but 55 ohms is believable. 55 ohms is believable, and that's the answer. "55 ohms, huh? Is that what they're saying?" Yeah, that's what they're saying. And you know what? It works. It works. You'll get, let's see if that actually works. Is R being 55 ohms going to make that, is R being 55 ohms going to give you 75? 55 ohms right here, remember it. 55 ohms right here. We're claiming 55 ohms is the answer. So we're claiming that 55 ohms is the answer. So what we can do is 55 ohms right here. 55 and 5 is 60. 60 times 30 is 1800. 55 and 35 is 90. 1800 divided by 90 is 20. 20 plus 55 is 75. Sure works. Okay? But you had to go to the quadratic formula, and like I said, for the quadratic formula, this guy right here, the r squared is really 1r squared. Everybody, notice how everybody's in terms of plus. You know, it's going to be x is equal to the opposite of b. The opposite of b. Well, the b is negative 10. Plus or minus the square root of b squared minus 4a. And that's a mess. Negative 2,475 over over 2a, 2 times 1. Okay, I mean, it's a mess. It's a mess. But it's going to give you 55 for one answer and negative 55 for the other answer. Only the 55 works. All right, that was 13. 15, find the current in the 12 ohm resistor in the figure. They're purposely asking us a very interesting question that kind of forces you to know a lot of stuff, which is nothing wrong with that either. Find the current in the 12 ohm resistor for number 15. So what's going on? Well, it's going on what's been going on in the past. Let's get the total current that's going to leave this, and the same total current is coming back. Whatever leaves here is going to come back to here. Yeah, but it's going to go through a lot to do that. And this influences how much current actually goes and comes back. But whatever does leave, here's the total. Whatever leaves is coming back. And it's going all over the place. Tell you what I'm going to do. Let's find that total current, and then let's play a bunch of games, I guess you could say. You could do this. This guy right here is going to catch all the current that goes through it, that goes through here. That current going through here is going to go through him, no more, no less. And this current coming in here is the same current that was leaving here, and the same current that's leaving in totality is going to go through this one, no more, no less. Everything else is kind of interesting. Tell you what I'm going to do. There's parallel circuits all over the place on top of parallel circuits. Why don't you find out the equivalent resistance on top and find out what's going on here. So here we go. What's the equivalent resistance here? Let's just take a look at this guy. The 6 ohms and the 6 ohms. 1 over R. You know, I don't want to leave too many subscripts. Let's just call it what it is. Let's get an answer and let's move on from there. Here's 6 ohms. Here's 6 ohms. 1 over R is 1 over 6 plus 1 over 6. You add them together, you got 2 over 6 right off the bat. 2 over 6 is 1/3. The equivalent resistance, get the reciprocal of each one. The equivalent resistance here is 3 ohms. So, I mean, I don't exactly want to erase too much of this, but if this is 3 ohms, the equivalent resistance there is 3 ohms with what is going on here. Okay, good enough for me. If this whole thing is 3 ohms, what's 3 ohms in series with 3 ohms? 3 and 3 is 6. So the top becomes 6 ohms. What about this one? Well, let's do another R here. 1 over R is 1 over 4 plus 1 over 12. It's a different one. Is 12 the same as, is 4 the same as 3 over 12? Is 1/12 1/12? Add them together, you get 4/12. 4/12 is 1/3. R equals 3. The equivalent resistance here is 3 ohms. Wow, just like the other one. That's kind of interesting in its own right, you know. The math is the math, though. I mean, let's make sure we did the math right. Yeah, it looks good to me. Looks good to me. All right. So that's, as we said, this is 3 ohms. What's 3 ohms and 2 ohms? 5 ohms. Five ohms, okay. All right, I think we've made it a little bit easier to look at. The process, it's not a difficult process, guys. It's Whole lot of detail done over and over and over. Sometimes that happens. Right. So you got this, you got this. You're about to go here. Looks good to me. Well, I'm answering and perhaps I'm answering too many questions. You know, I don't think I am though. I mean, I think you kind of get stuck with this stuff a little bit, and you are where you are. I mean, let me just make sure we got this straight, you guys. Yeah, it looks pretty good to me, man. It looks pretty good. So what do we got? Let's get the 6 and the 5, guys. Uh, 1 over 6 is the same as 5 over 30. 1 over 5 is the same as 6 over 30. That's 11 over 30. Over 11, which is 2 and 8/11 ohms. What's 2 and 8/11 ohms and 3 ohms? Right. I mean, it looks good to me. I mean, what you did was you brought this into an equivalent single resistor. The single resistor is in series with this. This plus this is going to be 5 and 8/11 at the end of the day. Now, if that's the case, what's the total current going through? I mean, you're basically doing something like that for so much of what we're doing on this stuff, guys. So what do we got here? We got the 18 volts divided by the grand total resistance. Take that to the degree of accuracy you wish. And that's going to give you the total amps. So almost equal to pi. That's kind of neat. 3.14286. That's the grand total. They didn't really ask us. They didn't really ask us that, but they could have asked us that, and we'd have to be able to do it. They asked us that. We got to be able to do it, and we can. We just did it. We can do it. It's a lot to be said here, guys. So now you work your way backwards. And I think the way out of this whole mess is that in totality, the 3.1428, the 3.14286, the 3.14286 amps is going through all of these guys. Well, right here, they're almost split evenly between them. This one gets more than that one. This one gets more current going through it than that one because there's less resistance. How much more current does it get? 6 over 5 times more current. If this guy right here gets X, This one right here gets 6/5 times x. And together it's the whole thing right there. So let's find out what's going on at the low end. And when we find out what's going on at the low end, we can come to here. Wow, it's a mess. So let's see what we can say. So what we're doing is, get some more chalk, guys. So what we have yeah, it's as simple as that. Look, there's the kind of like the grand total thing going on here. They're almost evenly split. This thing almost gets split in half between upper and lower. Lower is going to get more because it's got less resistance. If the one with the lower amount of current, because it has higher resistance, is X current, then 6/5 X current will be associated with the resistor with the lower amount of resistance. Low resistance means bigger current. Higher resistance means lower current. In totality, for that thing over there, you've got the one with the big resistance only has X amount of current going through it. The other one is going to get 6/5 more current going through it. This is 1 point, I'm sorry, forgive me. Yes, this is 1.2. This is 1.2x. This is 1x. Divide by 2.2 on each side. Here you're going to know what the high part was, and then you're going to multiply by 6/5 to know what the low part was, which has more current. The low part is what we care about because this is on the low side. This thing totaled to 5 ohms. The top right here totaled to 6 ohms. And that's all that's going on regarding something like that. So what happens is, and I did this, there's a lot of ways you could go here, I guess. Yeah, I mean 22/7 amps. Yeah, no wonder this they made. I kind of did it in terms of a fraction. So you could have almost, this is what I is. When we were solving it, we left fractions B as B, and we got 27/2. I'm sorry, we got 22/7. 22/7 amps, which is the same as this. 22/7 amps, which is the same as so they're identical. So that's it. I mean, what you got here is, regarding something like this, you're going to get what the X was. Well, if you go 2.2, if you divide by 2.2 on each side, divide this by 2.2, that's the same as multiplying, what would that be actually? That would be 22 divided by 10, that's 11/5. Is that right? Yeah, 11/5. You divided by 11/5. It's kind of interesting. 2.2x is the same as 11/5x equals 3.14286. I had actually used fractions more than, I don't know, maybe we can argue that a whole bunch of ways here. But here's how you can do it. Divide by 11/5 on each side. And it's a rather fascinating, divide by 11/5. Divide by 11/5 on each side, and you end up getting 10/7 on this one, or 12/7 rather, I'm sorry. No, let me not. Let me not take that back. X is 10 over 7 when you actually do that. If you were to multiply by 5 over 11 on each side, you multiply by 5 over 11 to get X. You multiply by 5 over 11 here. 5 over 11 to get here. That's 2. That's going to be 10 over 7. And then the other one, you go 6/5 times this. It's going to be 12 over 7. So this is 10 over 7 amps, and this is 12 over 7 amps. That usually doesn't come out too well, guys. I mean, to pull something like that. But it worked here. It worked here. Earlier in the mathematics that we were doing, this would have come out okay for us. Because we were in a situation where we were going, see, here's where it came from. This was this, and we figured out that that whole business, we said this and this is what? Well, how are you going to figure it out? It's 1/5 plus 1/6 equals 1 over R, whatever that is. And that came out to, right, that came out to 6 over, 1/5 is 6 over 30. 1/5 is 6 over 30. 1/6 is 5 over 30. It's 11 over 30. That's 30 over 11. We took the 30 over 11, which is the 2 and 8/11ths, and we added it with 3. And 3 was the same as saying, 3 was 33 over 11. And we ended up getting 63 over 11 for the grand total resistance. Now, if you took, how do we do that? Well, we said the voltage was 18. What is 18 divided by 63 over 11? There's a 9 in here. At the end of the day, there's 9 times 7. The 9 and the 18 cancel. There's a 2 here. That's 22 over 7. And that's where you got it's a little awkward. I just wanted to kind of backtrack, and just in case when you see it in the notes. It should come out straight with the notes, guys. I didn't use the decimals. For some reason, I jumped into the decimals in this discussion a little more quickly than what I did else in the other place here. But basically, this here is 7 times 9. The 9 and the 18 cancel. You got 2 over the fraction 7 over 11. The 11 flips upward. 2 times 11 is 22. 22 over 7. 22 over 7 is the 3.14286. So that's where that stuff's coming from, guys. And if you're going to break these up, 10/7 of it is one place, and the other 12/7 of it is the other place. And that is along the ratio of this one being 6/5 of what the smaller one is. Smaller one is X, this one is 6/5 times X, and the mathematics yields the small one being 10 over 7, and that was the one with the bigger resistance. That's the one. This is 10 over 7 amps up here. This is 12 over 7 amps down here. 12 over 7 amps is going all the way across this stuff. 12 in totality, 12 over 7 amps. Well, let's find out what's going on here. 12 over 7 amps, what's happening here, guys? So there's a number of ways you can go, but it's, it's a little bit, it's out there a little bit. So 12 over 7 amps, or were there numbers I put on there? I didn't really put any solid numbers on there other than good fractions, which are actually the most accurate of all, because this stuff repeats, goes on forever. There's no real good decimal expansion that's going to get you there. So you got what you got there. We could say a bunch. Just want to see how I kind of cut to the chase on the whole thing. The lower one has got 12 over 7. Now we said we've got going through this thing in totality. In totality, this guy's going to get the 12 over 7. In totality, he'll get the 12 over 7. Yeah, true. And this will get all 12 over 7. All 12 over 7 will go through here. But if this gets all 12 over 7, what do we have to say? I'll tell you what, the bigger resistor has less of this. 12 over 7 is the grand total. 12 over 7 is the grand total. 12 over 7 amps is the grand total here. Through all of this. Yeah. 12 is 3 times bigger than 4. 12 ohms will get, 12 ohms is 3 times the resistance as 4 ohms. Therefore, it'll get 1/3 the current that this guy gets. Of this whole 12 over 7 amps, this guy right here is going to get 1/3 as much as that one right there. And that's the way to go. What do we mean? Well, if this guy gets X current going through it, this guy gets 1/3 the current going through. This guy's got 4 times the resistance. Forgive me. 12 has 3 times the resistance. 12 is 3 times bigger than 4. 12 is 3 times the size that 4 is. 3 times the resistance means 1/3 the current. If the 4 amp gets X amount, if the 4 ohms gets X amount of current, the other guy gets 1/3 that amount of current. And altogether, it's this guy, the bottom guy. Remember, they both add up. This guy right here came out to 10/7 amps. Yeah, he did. What's 10/7 amps? What's 10 over 7 amps plus 12 over 7 amps? 22 over 7 amps, which is 3.14286. 3.14286 amps. This is 10 over 7 amps associated with this, and this is 12 over 7 amps associated with the bottom. 12 over 7 amps associated with the bottom, and 10 over 7 amps associated with the top. Why is 12 over 7 amps associated with the bottom, which is certainly bigger than 10 over 7 amps? Because the bottom has associated with it only 5 ohms of resistance in totality, whereas the top has more ohms of resistance associated with it in totality. More ohms of resistance means smaller number. The one associated with the top is a total of 6 ohms, smaller answer than the one associated with 5 ohms. And that's where we get this. So you add the two. This is 3 over 3. This is 1 over 3. See, these fractions work pretty nice. You know, sometimes they don't, but these sure do, don't they? Multiply by 3/4 on each side. Multiply by 3 over 4 on each side. 3 over 4, that's 9/7 amps. And that's the one that's one of them. And the other one is 3 over 7 amps. Why? Because what's 3 over 7? What's 3 over 7 plus 9 over 7? 12 over 7. Oh, by the way, that is 1/3 of that. If the answer is 9 over 7, take 1/3 of the answer, you'll get 3 over 7. Finally, we can get a decimal here, I guess you could say. The I associated with the 12 Okay, yeah, I mean, there's a lot of ways to go. I mean, we kind of left this one by the wayside. Notice it is really close to pi. Yeah, that is a good approximation to pi, actually, when you are dealing with fractions. 22 over 7 is a pretty decent approximation. It gets used sometimes when you're using fractions. It can get used sometimes, I guess you could say. 22 over 7 amps is 3.14286 amps, roughly. Okay. That's 15, guys. All right, let me cut it real quick, and then I'll put some more problems on the board, and we'll go for it some more. Okay, guys, let's continue. I put up 2 more problems here. We've already done 4 problems. And like I said, here's 2 more problems for us. Problems 23 and 30. For problem number 23, they're saying, that's over there on your far left. For problem number 23, the circuit in the figure, for that further circuit in the figure, determine A, the current in each resistor, B, the potential difference across the 200 ohm resistor, and the power delivered by each battery. Okay, so it's a lot that has to get done for this to work. It's a lot that has to get done for this to work. So one thing you can say is, let's pick the currents and their directions, I guess you could say, as we wish. I mean, I'm going to call this guy call that I200 going up. This guy we'll call I80, also going up. This one we'll call I20, also going up. And kind of surprisingly, there is an arbitrary nature to this, at least as far as you're proposing to solve the problem. We'll call this I70. I70 is going through the 70 ohm resistor. I20 is going through the 20 ohm resistor. I80 is going through the 80 ohm resistor. And I200 is going through the 200 ohm resistor. You're going to take all of the currents as going upward, with the exception of this guy going downward. So they all go, all of these go upward. They end up coming over here, and all of them merge together to equal this one going downward. All 3 of these go upward. They merge together somewhere, and when they finally merge together completely, they end up going downward in totality, and that's equal to I70. So what's going on is I-200 plus I-80 plus I-20, all those together, yeah, that's one equation for you right there. Let's call it equation 1. For equation 2, let's take a look at the I-200 and what's going on there. Well, the I-200 is right here. It's going through this resistor, so there's a potential drop because it went through the resistor. Then it works its way up here, then turns this way, and there's a number of ways we can go at that point. I mean, you could say, see what we can say here. All right, so let's play the game here. Let's start right about here. Let's take this guy. He's whatever's going on. It's right around here in this area, and he's firing right through here. He's firing right through here. The I-200 through here. Wow, there's a potential drop right there. So it's I times 2. It's a negative I times 200 or negative 200I. All right, let's put the numbers in front and the letters behind. It might be easier. Negative 200 I-200. There's a potential drop. Let's go. Let's start right about here or close to here or whatever, and let's start here. In fact, let's just go all the way this way and see what happens. At least right when it breaks off from here. So start here, go around. It's negative 200 I-200. Negative 200 I-200. Negative 200 I-200. Come around here. Come this way. Come this way. Come this way. It's going to go through the battery. But the battery's not going to help it. The battery's going to fight it. So at that point, we say it's negative 40. As we keep going. Now, here, the circumstances are rather interesting. How the whole thing plays out, I guess you could say. So it turns that way. I think of a good way, just a good way to say this. There's basically a pushing war, and at the end of it, this will go through the battery. This will go the other way through the battery. As you come this way, this guy's going the wrong direction. Not the wrong direction, or at least vis-a-vis the path I'm taking. It's a different direction. I'm going from a high potential to a low potential. So, forgive me, I'm going from a low potential to a high potential according to the path I'm taking. Path I'm taking is clockwise. Let's see, yeah, that would be clockwise. So, coming this way. So, you come through here, from a low potential to a high potential, you gain. And that's where they're coming from in that regard. So, what you end up getting here is plus a negative 40 or minus 40 plus 80 according to the path, all the potential drops, potential gains, everything, they got to add up to 0. Well, what's going on here? You drop here, but you gain here. And that's the argument there. Now, okay, so let's write that. There's a number of ways to write that. Let's add a positive 40 on each side and then take it from there. So what you're looking at so around this path, whatever hindrance and whatever gain is made, it's a lot of ways you can look at it in a sense. You could say that this is, vis-a-vis the tug of war that's going on. This is indicative of a gain in potential. It's going the right way vis-a-vis the battery. This one's going the wrong way vis-a-vis the battery. The difference between the two has got to be the battery. That's another way to look at it. So you look at that. Here's 2. Here's 1. Okay, so we got that. Now what about the other one? The other one's saying this. Depending on the paths we're going to take here, guys, we're going to go with the I-40 again here. So we'll say for 3, we're coming up here. We're going to go here. We're going to lose potential. So see exactly what we're going to say here. I guess you can say here. Let's stay with the I-80. I guess you could say. Exactly how I want to talk about this one. Okay, here as we go up, let's go up this way. Now, again, we went down this way. That was another story. We were going down this way. They got to be able to cancel. So this one was a gain. As you go this way, it's a loss. So this guy going up, following the path this way, clockwise again, go from here to here, it is a potential drop. It's negative 80 times I sub 80. Negative 80 times I sub 80. That's the amount of drop. There's a gain of 40. Then you come around, there's a gain of 360. And then going this way, as you follow this path, contrary to what's going on here, when you're going contrary to the current, you're actually gaining. So here, as we said, when we were going here, we were going contrary to the current with the first loop, contrary to the current, making a gain. Here we're going with the current, there's a loss. Well, with the current, loss, then a gain, going against the current, a gain again. So when you add all that together, you guys, what we end up getting is, we get negative 80, I sub 80. We get 40. We get 360. And we get that gain, a rather odd gain, but that's the way the gains happen. If you combine like terms and get, if you take the 40 and the 360, get positive 400, add a negative 400 on each side, and then kind of set it up, because that's what we've been doing more or less, you end up getting that's the third equation that we can talk about. Let's go. Let's start here and come all the way around. Go through here, you're going to lose. Go through here, you're also going to lose because you're going against the battery. Go around here, you're going to lose again and lose again. Let's see here, it's going to be quite a bit. So what I got here, so let's see here. We went counterclockwise. Unless I didn't go counterclockwise with this one. Let's have a look. We went from here through here, going with the current, so there's a drop. 20 I sub negative 20 I sub 2. Then, okay, for some reason, oh, there it is. Okay, I can see it. From here to here, there's a drop. Negative 20 I sub 20. Then, negative 360. Come around. Go through here. Negative 80. So, for some reason, as we said here, guys, I was trying to, did I put, for some reason, I shouldn't have put I think my notes might be off on this one. Yeah, I did something wrong with the notes. This should also, and then that's a negative, and then this is also a negative because it goes through this way, so it's a drop of 70. I didn't quite write that in the note. There's something wrong with the notes on that one. But in the end, it came out okay. So just want everyone be aware of that. The 70 I 70, the 70 I sub 70 should be negative 70 I sub 70. When you add all that up and get all the numbers over to one side, you should get this. What was that? I mean, there were negative 360 and negative 80, that's negative 440. It was a negative 440. Add a positive 440 on each side, you got this. For some reason in my notes, I had a positive 70 in one place, but then afterwards in the notes, I have it right. I mean, the final conclusion for that particular fourth equation is this. What is going on here? There are 4 unknowns. There's I sub 200, I sub 80, I sub 20, and I sub 70. Right down the line. I sub 70, I sub 200, I sub 80, I sub 20. There are 4 unknowns. I have 4 equations and 4 unknowns. Great candidate for Cramer's rule. I mean, you can do a whole bunch of stuff to do this, but Cramer's rule is probably, can be the easiest, I think. 1 through 4 are 4 equations and 4 unknowns. Do the appropriate substitution, you guys. What did I do here? There was a substitution. I did make substitute 1 into 4. What I did was I took equation 1. I sub 70 equals I sub 200 plus I sub 80 plus I sub 20. I took that and I plugged that into equation 4. I put the I sub 70, for I sub 70, I have this sum of these 3 items. I sub 200 plus I sub 80 plus I sub 20. Put that in here, grind it out, get them together, and then you knocked it down from 4 equations and 4 unknowns. Though you could do it, it's not as easy, but you could do it. You could do 4 equations and 4 unknowns, but we took it down from 4 unknowns to 3 unknowns. So instead of 4 equations and 4 unknowns, you have 3 equations and 3 unknowns. When that's the case, a number of things that happen. Let me show you. We'll show you some of the highlights, I guess. Just be careful with what the heck is going on when you're doing this, when you're following the path, you guys. With the current potential drop against the current potential gain when you're doing the path. And you're saying basically, you know, that's essentially what's going on when you're looking at this thing. They have to all add up to zero in the end. I mean, everything adds up to zero when you're going around a closed loop. There's no gain or loss. All the potential drops will add up to zero due to conservation of energy. Because of conservation of energy, when you go around a closed loop, for any closed loop, if you do the accounting correctly, all the potential, all the potentials accounted for, all the potential drops accounted for, they all add up to zero. Potential drops, potential gains, they all add up to zero. It's a pretty fascinating conclusion. It really is, and it works. So you got this right here. You substitute equation 1 for I sub 70 into equation 4 for I sub 70. And now you go from 4 equations in 4 unknowns, which you certainly could have done. Vis-a-vis Cramer's rule, just as is. You go from there, you go to 3 equations and 3 unknowns. But I see a lot of things that are multiples of 10. So I can write the whole thing down. And I have this in the notes, guys. They're going to scroll for you. So when you look at it, it's not going to be something completely foreign to you. You've seen it. When they scroll for you and you see it in your notes that I've provided in other places, you end up getting, you know, at the end of the day, you end up getting 3 equations and 3 unknowns. Make sure I wrote that down correctly, guys. We got, as we have it written, yeah, everything looks good. You've got that. Then you've got, we try to like line these up a little bit, I guess you could say. Some of these are a little more simple to look at than others. Despite that, there is a good challenge in there. There it is. Now, guys, look, this is a multiple of 10, as is, you know, the 440 is a multiple of 10, as is the negative 70, as is the negative 70, as is the 90, as is the 200, the 80, the 40, the negative 400, the 80, the 20. Guys, I can do a lot of things here, actually. I can divide each side of this equation by 10. I can divide each side of this equation by 10, and I can divide each side of this equation by 10. And what happens is, you guys know where I'm going. I mean, well, actually, I'm going a number of places, actually, is where I'm going. Okay, guys, I did this in different steps here, so I want to just kind of be careful. Yeah, it gets somewhat easier. What happens is I think I erased something more than I should have. This is 40. Remember, this was 400. This was 40. This was 440. This was 40. This was negative 400. Okay. Why don't you divide the bottom here by 2 all the way across? You keep dividing. Divide the bottom by 2. I wrote this in different manners here. How we do it. This ended up being 0 times I 200. If you want to just kind of keep it rigorous that way. This is 0 times I 20. Negative 7, negative 9, 44. Can't do anything about that. Here's a 20, a negative 20, and an 8 and a 4. How about divide by 4 on each side? We had 20, negative 80, and 400. Let's see here. We had negative 400. We had negative 80 here. Let me just go back, guys. I'm sorry. And we had 20 here. The notes are probably going to make a lot more sense than I'm making right about now. Divide by 20 on each side. Divide this by 20, you got 1. Divide this by 20, you still got 0. Divide this by 20, you got negative 4. Divide this by 20, you've got negative 20. Okay, that's what they meant. Okay. All right, guys, sorry. The notes tend to make a little more sense than I do, except for one little slip up with the 70 here. That had to be going against it. You're dropping. It's got to be a negative 70. Negative 70 ohms times I sub 70. Negative 70 ohms times I sub 70. And that, I corrected it later on within the same notes. So you're here. You got something looking like this. As you got this, and this one came to 1. All right, it's looking like that. 3 equations, 3 unknowns. Go ahead and solve it, guys. I've got it set up in different ways. I mean, in the notes, I got them in order. I got 20, 80, 200. It's not a big deal. As long as you stay consistent, the answers it gives to you are going to be consistent. But when we actually do this, so I put it in order. Does it matter? No, as I said, it doesn't. Could have left just what I have here, but I'm trying to keep some kind of consistency with the notes. Negative 9 I sub 20 plus negative 7 I sub 80 plus negative 7 I sub 200 equals 44. Again, just keep the bookkeeping under control. I just put the I sub 200 all the way to the edge. That's how I did it in the original notes that you're going to see scrolling. So there's nothing really fancy here, guys. Just break down the, did you have to do this? Could you have left the equations as they were and gone 4 equations and 4 unknowns? Sure. It's a lot more tedious. It's a lot more tedious. There's just more there, to kind of look out for. But there's 3 equations, 3 unknowns. I did it via Kramer's rule. We looked at it. Now, again, I gave my initial guess, and I did it with Kramer's rule. You don't have to do it with Kramer's rule. When it gets down to 3 equations and 3 unknowns, there's a lot of ways you can manage this and make it work, and you don't need to go to Kramer's rule. You certainly don't need to do so, but Kramer's rule is a wonderful, powerful rule. Great theoretical significance, very useful. You can use it. You don't have to, though. You can do it the other way and get the exact same answer as you get with Kramer's rule. At the end of the day, we ended up solving as is. We end up getting, let's just see what we got. I get I sub 20 is negative 8 amps, and we got to talk about that. Negative 8 amps, what's going on here? I get I sub 80. Right? See, the I sub 70 is not going to be a great issue. You're thinking, what is he doing here? He did something. Yeah, he's answering 3 questions here. He's answering I sub, he's answering I sub 20, I sub 80, and I sub 200. And he kind of, you could say, well, look, what did he just do here? Well, he sort of took I sub 70 and got rid of it. Yeah, I purposely got rid of it. I thought it was easier to solve. Do this and solve it. Go I sub 20 equals something. I sub 20 equals something. I sub 80 equals something. I sub 200 equals something. If you add I sub 20, if you take I sub 20, I sub 80, and I sub 200 and add them together, negative 8 plus positive 3 plus positive 1 is negative 4. We're done, sort of. We've got this, we've got this, we've got this, and we've got this. Yeah, true. True, according to the setup, but the negatives tell me the setup is off. The real situation, if you got a negative 4 amps, in reality, it should be doing that. If you got a negative 8 amps, in reality, it should be doing that. And the other guys, I sub 200 and I sub 80, because they're positive, are going in the right direction. Are going in the right direction. So in reality, and but you got to add them together to get this guy. Then you say it. Okay, what's going on here? In reality, the blue tells you where I-70 is going. It's 4 amps up. The blue tells you where I-20 is going. It's 8 amps down. The other guys are going in the right direction the way they were drawn. And I got that in the notes. So 8 amps, the 8 amps is the real big one here, guys. And that is, basically makes sense that it would be the real big one, guys, that's running the show. Look what it's associated with. And that's not, let's not make too many conclusions that way, but okay, that's really the big one, guys. The other ones are not as, but still, just not as much as this one. Makes sense. 8 amps, bam, it's going to win everybody. At that point, the 8 amps pushing down this way will push this. The 8 amps pushing down this way will push 4 amps up that way, and respectively 1 amp this way and 3 amps that way. 1 amp up. So coming this way, 4 amps break off. 4 amps break off this way. 4 amps break off this way, and 4 amps break off that way. What happens? There's a total of 8. 8 amps, 4 of them go that way. 8 amps, 4 of them go that way, and go this, and just go straight up this way. 8 amps, 4 of them go this way, and go up that way. Then you got 8 minus 4, 4 amps going this way. One of them breaks off and goes 3 amps this way, and the other one breaks off and goes 1 amp that way. And it's in the notes, you guys. They're asking, find the potential difference across the 200 ohm resistor. Potential difference across the 200 ohm resistor. That's pretty easy now. Yeah, it's easy once you got all the currents. What's the potential difference? High potential, low potential. How much of a drop is there? Delta V associated with the 200 ohm resistor is 1 amp. 1 amp times 200 ohms is a 200 volt potential drop. Once it goes through the resistor, you lost 200 volts of potential as you take a walk. It's a fascinating process, I guess you could say, with the whole thing. There's other ways this can be looked at. In some ways, you could almost argue more intuitively, but a little more complicated, but also more intuitively, I guess you could say. There's potentially other ways you could look at this, but for our purposes, this is fine. How you're saying this here, what's going on? How does this around a particular path, given what's happening there? Can you analyze what has happened here? Everybody's got to add up within the path. The path does not necessarily have to be in the same direction as the current, and that's where it gets kind of messy. Certainly a lot you could say. Certainly a lot you could say there with that. But there it is. That would be, so 200 volts is the drop right there. And let me see the power delivered by each battery. What's the power delivered by each battery? Well, I times V. I times delta V is the power. So how much power is being delivered when 80 is going through here? Well, you got, I sub 80 rather. I sub 80 is 3 amps. 3 amps associated with a potential difference of 40. 3 times 40 is 120. Here, it's 8 associated with this. Right, 8 times this, big number. So let's see what they got here, guys. Let me just write them down here. Let's be kind of careful. I don't want to be too cavalier in what I'm saying here. But yeah, it is basically what I just said. So C, go down the line here, and what's associated with the power associated with it. There's batteries here. And what they're just saying is I times V a whole lot you could say here. I'm really tempted to try to say something regarding some of this, I guess you could say. There's other ways you can view this, and maybe perhaps down the road we can kind of give another look at this and still get the same answer, perhaps. If we don't, this is fine as is. This is actually fine as is. But there seems to be a bit of an intuitive look we could take at something like this and make some sense out of it, I think. That's neither here nor there. Right, for our purposes, right now, 23C, I times delta V or IV, and that's what we've been talking about. So when you got the 40, and I was pretty much trying to say that, might as well, the battery with 40 volts, the battery with 360 volts, and the battery with 80 volts. Three amps going through a battery that's got 40 volts, 3 times 40, 120 watts. The battery associated with 360 volts is also associated with the resistor that we talked about, what was going through that resistor, that 20 ohm resistor. That 20 ohm resistor had 8 amps going through it. 8 amps going through it, potential 360. 2,900, well actually no, forgive me. Let me think here. Right. What you would do here is good little, I mean, you could pretend this is 400, just the mathematics. 8 to this, let me think here. Yeah, you're coming out to this. Not too bad. 2,880 watts. The other one is saying there was 4 amps that went through the 80 resistor. 4 went through let's see that, for example. Let me actually see that. The 200, for some reason, what was that all about? That was 60, right. Right, for some reason I'm looking at different numbers here. I'm sure it's not an issue. We said the 80 had the 3. I got 320 for that one. I'm just not, I'm actually not, I'm sorry, I'm having a hard time believing what I just got for an answer. Oh, I'm sorry. Yeah, right, correct. This was a 4. I'm sorry. For some reason, I was associating with the 80 ohms. I was associating that with the 80 volt battery. This had 4 ohms. This one right here should have had 3 amps going through it, and we could have said what that was. Let me just see to be sure, guys. I don't want to. Just so we talk in the same language on this stuff. Right, that one ISB had 3 amps going through it, and we can work on that. And we actually got that answer, and that was the 3 amps right here. Associated with the 80 ohm resistor, but it's a 40 volt battery. Associated with the 80 volt battery, that was indeed 4 amps. That was indeed 4 amps. So yeah, I mean, that's pretty neat stuff. Whole lot of ways you can look at stuff, guys, in the process of what's going on here. There's a number of looks that can be given to this, but this is certainly fine. It works great, guys. So stay with it. Stay with it as we proceed with this. So, okay, with that in mind, nothing wrong with this whatsoever, guys. I'm anticipating, are there other ways people can look at this stuff in a sense? One can argue, I mean, a number of ways to actually look at something, but that's food for thought for some future date, I guess you could say. This is certainly fine. It is the standard of how you approach a problem like this. So by all means, this is the standard. Stay with this. When all else fails, be looking at it this way, and then the various ways to solve multiple variables, to solve n equations and n unknowns. There are a number of ways to proceed. Again, we used Cramer's rule on this. We didn't have to, but certainly would have worked. Let's go a little further. Let's talk about something else. Let's talk about problem number 30. For the circuit over to your far right in the figure, use Kirchhoff's rules to obtain, and they got a lot of stuff here. They go A through F on this thing. They want you to obtain equations for the upper loop, the lower loop, the node on the left side. In each case, suppress units for clarity and simplify combining like terms. D, solve the node equation for I sub 36. Using the equation found in D, eliminate I sub 36 from the equation in part B. F, solve the equations found in part A and part E. This is it's kind of all over the place. So it's a tough one to, I don't know, it's a tough one to read, and you got to kind of watch what's going on there. I think what is important about problem number 30 is that we can visualize very much of what's going on, and we can solve very many things, even if it's not entirely clear or easy to look at as to what they're asking us to do. We know enough, we can solve any of what they're asking us to do, as we were able to solve a lot right now on problem 23. So let's take a look at this right here, and well, I mean, there's a lot here. I mean, there's an upper node, a lower node, and they're just asking us a number of things there. Look, we've already done this sort of problem just now. We just finished doing this sort of problem. We've seen it in the notes before, and we just saw it on film here, and we're going to have more of it. You're going to have all this stuff scrolling through, so you're going to see problem number 23 again as it scrolls through. If I've got you in my classes, you can see it on Canvas as well. All right. So for 30, what are they saying? We're going to take the upper loop and go counterclockwise along the loop and see what we can do. Let's go up here, go counterclockwise around the upper thing, and let's see what we can say here about this whole thing. We got I sub 36, I sub 12, I sub 18. They gave us what they propose to be the directions. We don't know that they're the directions for sure. Heck, we proposed directions for number 23, didn't we? We proposed directions for 23, and we were able to solve the problem. We were able to get answers, But when we found negative answers, we said, hey, there's something wrong here. Just reverse the direction and then we're fine. But mathematically, everything was consistent. We got the answers. We didn't get what we wanted to get, but we knew what we needed to get, and that's everything to be positive. Then we had to reverse the directions. That's after we did all the mathematics, though. You don't mix and match that stuff while you're doing the problem. You do the problem, and then from there you draw conclusions as to what direction things are moving. Okay? What direction the current's moving at that point. Then you make that judgment. And you saw that we did that. You saw that we did that. So for this one right here, they're saying, here's I sub 12, goes through here, bam, loses potential. Then it gains potential. Then it loses potential. Then we climb up here, and we got I sub 18 going through this guy. Well, so it's dropping potential. Then it's gaining. Then it comes around here. Then it drops again. True. All right. Well, that was a lot. I mean, but let's just. So you heard me say what I said. There's a drop. There's a gain. There's a drop again. There's a drop once again. There's a gain. Equals 0. Okay. It's a mess. When you combine like terms, just wanted us to get it for the first one. Combine all the like terms. I got an I sub 12 here. Yeah, I also got one here. Negative 7 and negative 11 is negative 18. I got an I sub 18 here and an I sub 18 here. Negative 5 and negative 8 is negative 13. Negative 13 I sub 18, negative 18 I sub 12, and the 12 and the 18 add up to 30. So they add up to 30, and this is a negative 18, so there's a lot going on. Negative 18 I sub 12 plus negative 13 I sub 36. Is that, no, was it 12? Was it 18? I'm sorry. Negative 13 I sub 18, negative 18 so negative 18 I sub 12, negative 13 I sub 18 plus 30 equals 0. True. Leave the plus 30 alone, add a positive 18 I sub 12 and add a positive 18 I sub 12 on each side and add a positive 13 I sub 18 on each side. So what you got is add a positive 18 I sub 12 on each side, add a positive 13 I sub 18 on each side, and you basically got this. You got absolutely. Can you do that? Can you do that for the lower loop? Yeah, I mean, it's the same process. The lower loop, you're going to do it again. You're going to cross over there. You're going to go this way, cross over that thing, and that's a negative 11 I sub 12, positive 12, and a negative 7 I sub 12. Coming around this way, you're going against this, so it's negative 36. Let's see here, make sure I'm going clockwise. Right, counterclockwise. Okay, forgive me. Let me go counterclockwise. I went counterclockwise. It doesn't really matter. Won't matter because this will be a negative 36 if you go clockwise, and this will be a positive 5I36. But if you don't go that way, this will be a negative 5I36 and a positive 36 that way, and then coming across, see, yeah, the numbers get a little different. It doesn't really matter. I think maybe this is an important thing. Let's purposely do that, actually. Let's purposely look at this two different ways and get the same answer. Maybe that's a good thing to do. There's A that we talked about, right? Let's do it. Let's go clockwise. Let's go clockwise first, see what it does. From here to here, going with the current, huh? Yeah, following the current, that's a drop. That's negative 11 I sub 12 plus 12, negative 7 I sub 12. Negative 11 I sub 12. Negative 11 I sub 12. Negative 11 I sub 12. Right. Drop here. Negative 11 I sub 12. Picks up here, then drops again. Come around here, follow the path. Yeah, go against the battery. All right, go ahead. Go against the battery if you wish. It's plus a negative 36. Go here, go against the current, you're going to gain. Because you're going to a place where the current was, and it was at a higher potential where the current was. There you go. We just went clockwise. Let's go counterclockwise. Counterclockwise, huh? All right, let me see. I'm going to try to make this easy somehow. All right, so I went this way. That was clockwise. I went clockwise and did what I did. I went clockwise and did what I did. Clockwise and did what I did. Now let's go counterclockwise. Let me start here where I ended. Let's go. Well, I'm going this way, I'm losing. It's plus a negative I36. Yeah, look, at the end of it, they all got to add up to 0. Remember that, so I'll do that too. Let me start here. Let's go counterclockwise. Let me go across. Bam, I'm going with where he's going. I'm going with where he's going. That's negative 5 I36. Go here. Gain 36. Give myself a little room, guys. Okay. We'll figure it out. Plus, so that was a plus right here. Where'd it come from? All right, I got here, 36. Let me go up here. Let me go against the current. So it's going to be plus 7 I12. Okay. Then I'm going to go against the battery. Then I'm going to go against the current. Or at least go look at my path. What is going on here? How do these potentials work out? I'm trying to account for what the potential differences are. What's a higher potential difference up here if I go that way? So it's positive 11 I12. Bingo. It looks like a mess, and it is a mess. I'll be the first one to admit it. But there's reason behind it. 0 is 0. 0 equals 0. That's the easiest part of the whole thing. If you took all of this and multiplied by a -1 all the way across on both sides, multiplied by -1, that becomes this. This becomes that. This becomes that. Multiply all of this by -1 and multiply 0 by -1. Multiply by -1, it's still going to add up to 0. Multiply all of this by -1, and it's going to add, multiply all of this by -1 and multiply this by -1, and you still got 0 equals whatever the result of the multiplication is when you multiply by -1. Multiply all this by -1. Multiply this by -1, you get 0. Multiply all this by -1. -1 times this is that. -1 times that is this. -1 times that is this. -1 times that is not that. It should not be that. Let me see here. Let's see what I did. Went against it. Went counterclockwise. That should have been a positive 36. I'm sorry. That should be okay. Let me... Right. Going with it. Correct. It would have dropped and then gained. Yeah, gained 36. My mistake. We caught it. Multiply this by -1, you get 36. Multiply this by -1, you get this. It works. It works. So either one is fine. You see that they're fine. Doesn't matter if the opposite of this, this is all 0. The opposite of it is still 0. This entire mess adds up to 0. What's the opposite of this mess? Well, if you take the opposite of each, if you take the opposite of everything that's being summed, yeah, if you take the opposite of everything that's being summed, it's going to be the opposite of the sum. Well, the sum is 0. The opposite of 0 is 0. Well, let's see here. You add these together. 7 and I12, 7 and 11 is 18. 18 I12. That looks familiar. $36 only occurred one place. This 36. Here we got this, 24. At the end of the day, yeah, we got the 5. You can do it any way you want. You got this right here. Now, here's what I'm doing. Here's what I'm going to do. It doesn't matter which one you use, guys. This right here is -24. Add these together. 12 and -36. 12 and -36 is -24. -24. Add a positive 24 on each side. All that's out of there. You got a positive 24 right here. This right here is positive 5I36. And this is -18 I12. Yeah, that's about right. So what we got here for B sounds good. C. That's A and B. C. Solve the note equation for I36. For I36, huh? Well, yeah, it's an interesting matter in its own right, right? According to what I got set up here, I got I36 racing to this corner and then taking a turn to go upward. And I got I12 racing to the above corner and then making a turn. I mean, they're going to meet up. When they meet up, they'll be as big as I18. I18 is composed of I12 turning this way and I36 turning this way. Look, they're not going to go any further. I mean, I12 is going to make it all the way to here, and I36 is going to make it all the way to here. I12 makes it right here. I12 makes it right here. I36 makes it right here. And those two come in here, and what comes out is I18. So what we got is I18 equals I12 plus I36. Sounds good to me. That's C. Okay, so to do it for I36 is not that bad. I mean, once I got I don't know, the way they kind of, this is the way I gave the answer. The way the question is actually phrased is not, to me right now, it's not very clear, but that's, you're finding equations here, and this is fine. I'm sure the key agrees with this as well. To find for I36, I'm just going to use what I did here for C, and simply say I sub 36 is I sub 18 minus I sub 12. I sub 36 equals I sub 18 minus I sub 12. Yeah, that's fine. Again, it's a little, the question itself, I don't know. It's a great question in many ways, and perhaps the way it's being asked could have been phrased differently, but it's nonetheless a great question. That's D. Using the equation found in D, eliminate I36 from the equation found in B, and then for F, solve the equations found in A and E. Okay, this stuff is kind of easier done than said, guys, what they're doing here. All right, so you got what you got here, guys. We're looking at this. Pretty fascinating stuff. I mean, it's not, and I could argue with you that there's, I don't want to be too bold here, but there are usually a number of ways to proceed with so many of these problems, guys. Again, the standard that they're kind of setting is really good, though. So for the most part, play it safe. The way they're going is really good. So you're looking at what we got here. We did all the way through D, and so what are they talking about? Using the equation found in D, using for that, for D, using the equation found in D, eliminate I36 from the equation found in B. Okay, so B is looking like this. True. And we did say that I sub 36 is I sub 18, I sub 12. Wherever you see I sub 36, put that. You're eliminating, that's all they're saying. I mean, they kind of, the way this stuff is phrased sometimes, or just by virtue of the volume of what's being said, it's more confusing than it actually is. I mean, it's really not that bad. You know, tinker with this a little bit, and we'll see where it's at. Negative 5i12, this is positive 5i18. Positive 5i18 minus 18i12. So I don't want, actually I took the wrong one out of there. But again, the premise is pretty standard. This is 5i18. Leave it alone. There's nobody to really mess with it. 5 times negative I12 is negative 5i12. Negative 5i12 minus 18i12 is negative or minus 23i12. Or plus a negative 23i12, 14. Stuff's not too bad, guys. There it is. For F, they're saying take what you just did, this one, and this is what we just did. Earlier we did this. Correct, right? The order's kind of messed up, but that's all right. Let me. Right, and that's what we had done that. We did what we did for E. For B, we already did something, and we made it. Trying to figure out where we did something here. I know we did this somewhere. Right. For A, we had 18I12 plus 13. For part A, ladies and gentlemen, we did 18I12 plus 13I18. 18I sub 12 plus 13I sub 18 equals 30. And that's this. Now, obviously a better way to do it is 13I18, put it right over here. The 18I12, put it right there. And then solve it. It's the easier way to go. I mean, so you saw it. We did it. This is the first thing we did. That's why I forgot we actually did it, guys. Yeah, it was 18I sub 12 plus 13I sub 18 equals 30. That was part A. All right, and we erased that, but we have it in our notes. We have everything. And we've got this, and the 18I12, put it right here. And the 13I18, right. Yeah, see, I kind of did this a little differently. It doesn't really matter. The order that you're going to have these here, 13I18 and then 18I12. And of course, I usually, the way I did it was I had the 18 I-18 over there and the 13, the 18 I-12 over there and the 13 I-18 over here, and then also the 5 I-18 over here, the negative 23 I-12 over there. It doesn't matter as long as they line up, you guys. Solve 2 equations and 2 unknowns and you're done. Solving 2 equations and 2 unknowns, you're done. Well, negative 0.416a absolutely. Yeah, be careful. Let's not make a move on this yet. Let's talk about G. G is saying I-36 oh yeah, there's a G. Yeah, there's a G on the other side. And they talk about what's the significance for H. So there's a whole lot of stuff here, guys. What we can say let's talk. What we can say is, should go pretty smooth actually. We got what we got here, and I-36 equals I-12 minus I-36 equals I-18 minus I-12. I-36 equals I-36 equals I-18 minus I-12. Notice I've not made any funny moves yet, guys. I know there's something up here. We've got enough experience. We know there's something we got to look out for right here. This is fine, but let's just leave it alone. Do the math as the math is occurring. At the end, you square up what the directions are. At the end, you'll square up the direction, not in the middle of it. I said that on problem number 23 just before this, and I'm saying it now. Just before this, we said don't be messing with the mathematics until the very end. Get the answers as they are coming to you, regardless of negative or positive or anything. At the very end, kind of determine what the directions are. Not in the middle of the problem. Not in the middle of the problem. Same thing here. Let's take this thing seriously and play the game. What is I sub 18? What is I sub 18? What's I sub 18 minus I sub 12? This minus a negative is plus. And it becomes 3.286, something like that, right? I mean, 3.286, roughly 3.3 amps. This is a correct answer. There's nothing wrong with this answer. This is correct, period. Well, you can say, what are you talking about? How can it be correct? It came from this, and that's not right. The mathematics yields the right answer. If that would have been a negative, I'd have to switch it at the very end, at the very end. This is fine. This is, as I said, you're going 2.88 minus a negative 0.416. Minus a negative is plus. Minus a negative 0.416 is plus 0.416. If you do that, you get pretty interesting stuff. Let me just see here. 0.12, 0.3, but not quite, 0.286, something like that. It should be about 3.286, so they made it 3.3 amps right there. Everything's fine. Everything's fine. The direction here is correct. Direction here is correct. I-18, that is also correct. I-12 is actually the other way. You do that after the fact. They're asking us here, that's G, that's H. Flows in opposite direction of what is shown. I sub 12 is 0.416 amps to the left. It has to go to the left, and that's H. That's the answer to H. What's the significance of this? Significance of this is all the mathematics. This is all sound mathematics, as it was in the problem before this problem. All the mathematics was sound, and it got us what we needed to get. At the end, we square up the directions. At the very end, we square up directions. No other time do we square up the directions. Do the mathematics. As long as you're consistent with the mathematics and doing it correctly, everything is fine. At the end, you can talk about the directions. If things are positive, your initial guess was right. If something's negative, or if they're even all negative, or whatever's negative, if they're all positive, you guessed the right direction. Whatever is negative, you guessed the wrong direction, reverse the direction, and you're fine. Only at the very end. Only at the very end. Okay. That is 30. 31. They're saying find the potential difference across each resistor in the following figure. Let's take a look at it. Let me try to run through this, guys. This is taking a good amount of time, but I think it's worthwhile. That's why you got the fast forward button. That's why you can speed up things as well, I guess. So it shouldn't be too bad. Go back when you need to go back. Go forward when you need to go forward. Go fast when you need to go fast, I guess. You can speed this stuff up a little bit. But let's see what we can do. Given what's there, let's try to run through this. For 31, Okay, guys. Same kind of thing. Make some guesses. How good are your guesses? Well, they're either, it's either like a yes or a no. It's either one direction or another. That's it. It can't be. That's the thing with the wire. You only got two places it's going to go. Two directions it can go. So not too bad. Tell you what. Let's go. Let's kind of follow the argument here. You got this guy going. We'll call him I sub 12. We'll call this guy I sub 3. Counterintuitive a bit. Here's the way it wants to flow. Here's the way it wants to flow, and you're telling me it's going this way. Or at least I'm telling you it's going that way. Yeah, I'm saying 18 is pretty strong. 18 is probably going to overpower everybody. Maybe yes, maybe no. And then we'll say I-18 is this way too. Why is that? Well, because it's got to flow into here. The same thing that flows into here is what flows out of here. And if it's I-18 flowing into here, it's I-18 flowing out of here. So I-18 flows into here, I-18 flows out of there. I-3 goes down, I-12 goes down. I'm saying this guy overpowers the whole show. Am I sure? Initial guess doesn't mean I'm right. But that's the initial guess. We're thinking it's doing this, it's doing this, it's doing this. That's the guess. And we're following that. Well, I'll tell you what. Eventually, this I-18 is going to take a turn and head this way. The I-18, all this and all that, the I-18's going to come up here, take a turn, and go right here. The I-18 is going to break up into I-3 and I-12. Well, I think I just answered that. That answers a big question. We just said the I-18 breaks up into I-12 and I-3. Those two, it breaks up into those two. Okay. Now what? I got three unknowns, ladies and gentlemen. I sub 18, I sub 12, and I sub 3. Three unknowns. I got one of the three equations that I need. What's another one? Tell you what I'm going to do. Let's take a walk, and let's see what we can do. Let's go against the battery. Okay. Go against the battery, that means you lose 12. Then go with the current, go from here to here, that means you lose 5I12. So it's negative 12 minus 5I12. Take a turn, come up here. As you're going up, the way this guy's flowing, up here is a bigger potential. Down here is a bigger potential than over here. So as you go, you're going from low potential to high potential. So it's plus 3I3. Plus 4I3. Then you go through here, you're going through the battery. Okay. As you go through the battery, in your path, you're gaining 3. So what just happened here? Well, what just happened was this. You went clockwise. Forgive me. You went counterclockwise, and you lost 12. You lost 5I12. As you're going there, you're looking at how the current is going relative to the path that you're taking. So you're actually gaining potential on this one. Plus 4I3, and as you go through the 3-volt battery, you're gaining 3. And that's got to be equal to 0. Let's go over here. Just take the same walk, I guess. You're going counterclockwise again. Let's go through him. You lose. I mean, you're going this way. You're going against the battery. That's negative 3. And let's see here. You're right. You're going against the battery. That's negative 3. Then you're going down this way. You're going with the current. So you've lost. That's negative 4I3. So negative 3 plus negative 4I3. Go this way. That's negative 3 I18 plus negative 2 I18 plus 18. So what we get is so negative 3, that's correct. We want, again, let's see what we did again now, guys. Took a path, went against that. It's going to be negative 3. With the current, you're losing, so negative 4 I3, negative 3 I18, negative 2 I18, and this is plus 18. Let's just see here. Let me just see that again. Right, no problem. Looks pretty good, you guys. We're doing that. Here we go. So there's a lot, obviously, that you know, these guys are like terms. The numbers are like terms in a sense because there's no, you know, there's no variable associated with them. Same thing here. Like terms in the sense that they're just flat out numbers, and the rest is okay. All right, so you do that. So you put that all together, and that's it, guys. You're basically, I mean, I don't want to beat this up too badly, but I want to get us, at least give you the argument of how to get through this. You will see it in my notes, so I'm not going to be, I don't have to go into all the excruciating detail of it because I do have it in the notes in that particular manner. Let's, you know, there's a whole bunch of ways you can go, I guess. I'm just trying to figure out a way I could say it. They're all kind of a horse apiece, guys. The 3 and the negative 12 is negative 9. So you got negative, you know, I'll put the 4i to the, I'll put 4i sub 3 out in front. 4i sub 3 out in front plus negative 5. 4i sub 3 out in front plus negative 5i12 plus negative 9 equals 0. If you had a positive 9 on each side, you got that. I mean, there's a lot of ways to go here, guys. You know, you could put the positive 9 on there, add a positive 9 on each side, and you got that, or just leave the negative 9 as is. The argument's not, it's not too, either way, you can get there pretty easily with 3 equations and 3 unknowns. The bottom thing is negative 3 and 18. Negative 3 and 18, negative 4i3 take a look at it, right? Yeah. Plus negative 5 right, plus negative 5i18. You got this. Actually, a better way to write it is you got all this. Well, you got 3 equations and 3 unknowns, guys. You can proceed on that any way you wish. You can set them up in a whole bunch of ways. You know, the 3, 12, 18, 3, 12, Nothing there for the 18. 3, nothing there for the 12. There's the 18 there. A whole bunch of ways you can set it up. Once you set it up, those are the 3 equations and 3 unknowns. Once you've done that, and we've already said this, watch out. Don't make a big deal out of it. Get the answers that you get, and then we'll talk about what we need to do only at the very end. 1.846 amps. When you actually solve it, the I-12 is this. Remember now, I-12 and I-3 will give you the I-18. Get I sub 12, get I sub 3, add them together, you get the I-18. What if there's a negative? Who cares? We're not worried about that. 0.323 amps. Opposite direction of initial assumption. We'll cross that bridge when we need to. Right now, leave that negative as is. Do not change it. You'll get it wrong if you do. Add these two. You get 1.523 amps. That's right, and it's only right when you add these. In the end, you'll change that, though. The end, you'll change that. But not before the end. For right now, if you're going to get I-18 correctly, done, you have to stay with that. That was the assumption. That's how the mathematics is based. That's the only way you're going to get it. Now, what's the truth now? The period. And that's it. End of the story. You got this. You got this. These are true. Direction, size, everything. Magnitude and direction are right. This one only has the right magnitude. Not the right direction. So you got to straighten that out. Because it's the opposite direction of the initial assumption. So as is, it's not correct. All of it's correct mathematically, but then you got to account for that. This means, what does it really mean? It means 0.323 amps. 0.323 amps. Right here. 0.3, so right. Negative 0.323 amps. That's negative 0.23 amp. What does that mean in reality? You got to reverse it. It's got to go that way. But to solve it, you only do that at the very end. You solve with that negative. Like I told you to do in the last problem. Two, 3, 4, 5. What are the potential drops across each of these? Well, it depends on the current. 2 ohms, 3 ohms, 4 ohms, 5 ohms. Ohms, 2, 3, 4, 5. Sounds good. Give me the potential drop across the 2 ohm, the 3, the 4, the 5. Two, 3, 4, 5 ohms. Find the current. What's going on here? Well, it's 2 ohms. It's IR is the V. The delta V is I times R. The delta V is I times R. R is 2 ohms. The I across the 2 ohms is the I-18. The I across the 3 ohms down there. It's also 3 times the current. How about the 4? The 4's got the I3 going through it. Right? Yeah, there it is. And the 5's got the I12 going through it. All you need to do is plug in what I-18, plug in I-18 right here and do the multiplication. Likewise here. Plug in I-3, do the multiplication. Plug in I-12, do the, I-18, plug them in, grind it out, do the multiplication. I-3, I-12. Yeah, what am I going to do for I-12? Yeah, we said it's mathematically there's a lot of validity to it, but as a final answer, you got to give a magnitude and just switch your direction to get the direction straight. You got the magnitude okay. Well, if you plug in the values, in other words, put a plus in here. Put a plus 0.323. Put a positive 0.323 amps for I-12. A positive 0.323 amps. So when you do that, it just goes down the line, guys. Give it to us down the line when we do this. Grind out the numbers, guys. That's all it is. Let's make sure we got this right. Yeah, right. Right. 7.38. You're done. That's it. Plug in the numbers and go, guys. Should work. Again, the notes are here. Any gaps or any time I might have gone a little too fast, let's just get it right. We can do it. But went a little too fast for you. Again, the notes are present. The notes are present there for you. So scroll in at the end. Let's look at number 39. Number 39, what minimum number of 75 watt light bulbs must be connected in parallel to a single 120 volt house circuit to trip a 30 amp circuit breaker? How are you going to overwhelm it? How many would you put? What's the minimum number you could put in parallel to one another for a single 120 volt household circuit that's connected to a 30 amp circuit breaker? If it goes 30 amps or more, it'll break the circuit breakers. Let's see what we can do here. For number 39, how you do that? All right, guys, a number of ways to go here. Let's talk about a few things, what is and how to play this whole thing. We know that. Depending on how we're speaking the language, you see me write it like this sometimes. Watch out, just be aware of it. I delta V, or IV as I call it oftentimes, all these mean the same thing. Note, voltage in parallel is the same for all the light bulbs. The voltage in parallel, the voltage that they're experiencing is the same for all the light bulbs. So the voltage is the same for all the light bulbs. So I guess you could say I is equal to power divided by V, because IV equals power. What does that mean? Well, you have a maximum limit of 30 amps for I, and there's n number of light bulbs that are going to give you n number of light bulbs, each one with I current. They each have the same amount of current associated with them. But how many? I mean, well, let's talk. So there's 30 amps, that's the I. The I is 30. You're going to add from each one of the light bulbs I amount of current. Each one's got I amount of current associated with it because of the symmetry of the situation. The resistance is the same light bulbs, the whole thing. That's the same as N times P over V. Well, 30 is 30. N is N. Each light bulb expends 75 watts with the same voltage, because they're in parallel, each one has the same voltage. So if this is the power that they draw, and each has a voltage through it of 120 volts because they're in parallel, each one has the same voltage through them, each one's got 120 volts going through them, each one's got 120 volts going through them, and each one draws 75 watts. Power divided by voltage will give you the current in one of them. Yeah. N of them, this current in one of them times N of them will give you 30. N is N. Does that reduce to anything? Yeah, 15 goes into here 5 times, and 15 goes into here 8 times. Multiply by 8/5 on each side, or divide by 5/8 on each side, or divide by this ratio. Divide by this fraction on each side, and you'll still get N. No big deal. That's 8/5 times 30. Multiply on each side by 8/5. Multiply on each side by 8/5, and you get 48. That's 39. Let's look at 47. Calculate the potential difference between points A and B in figure that I'm about to write down, guys. That's A. Calculate the potential difference between those 2 points. Identify which point is at the higher potential, the A or the B. All right, let's write that down, and we'll take it from there. Almost there, guys, almost there. All right. Trying to figure out what's going on here. Let me draw this. Should be pretty straightforward. see what they're talking about. They drew a rather odd figure here, but let's play the game the way they're asking us to play the game, I guess. Uh, 10, 4, 2 over there. Yeah, 10, 4, 2. Looks pretty good, guys. All right, we got this. Calculate the potential difference between points A and B, and B, identify which point is at the higher potential. So you want you to, between points A and B, they want you to find, if where's the tendency for there to be more potential. All right. Since far right is open, no current is there. The far right is right here, guys. Far right here is right here. There's no current here, obviously, and there's no current over here. So, so that's of great interest, actually. So let's see what we're going to say about that. But far left is closed. And we can say what that is. So the far left, because all of this is open, no current here, but this is closed. What is it? It's in series. What's 4 and 2? It's 6, associated with a 12-volt battery. So the V equals IR is 12. V equals IR. 12, the I don't know. The resistance, there's a 2 ohm and a 4 ohm in series. Divide by 6 on each side. Well, we know that. We know that. So there's something of interest here. How are we going to do this? So we got the 2 amps that we talk about, and what's going on here? How are you actually going to do this? So you're trying to phrase it faithfully the way they're trying to phrase it, I guess you could say. Calculate the potential difference between points A and B. It's a hard one to call. I mean, but I say if you did connect something to it, what would happen? That's a good thing to say. I mean, what would happen? In which direction would, the flow of the current would depend upon which one's the higher, what direction of flow of the current would depend upon which point had the higher potential. If indeed there's a potential difference between them for us to look at. Okay, we said this right here. Between the two, there is a 4-volt battery and what happened there. So let me just see. Let me try to see here. The way it's being looked at, guys, is this. They're saying delta VAB is equal to, okay, whatever's going on here, there is if you did attach something here, let me see what we could say. They're saying for some reason take the 4-volt battery minus 2 times 4 here. So if you took the 4-volt battery, we'll see what the tendency is. Let's go with what they're going with. IR4. Well, yeah, I mean, wait a minute. 4 is the 4-volt battery. Nothing's attached to it yet. We're saying potentially you would attach something to it and we'd see what would happen. What would be something to say regarding that? So 4 minus 2 times 4, it's a negative 4. What's going on here? There's a potential difference (4 volts). From A to B was negative, point higher, point A at higher potential. So what they're saying here, guys, point A would be at higher potential to do something like this. So the way you'd want to look at it, I'm trying to think about, there's got to be a better way there. I'm not really crazy about the way this is put up together here. There's got to be a little bit more intuitive way to look at it, I think. From A to B was negative. Basically, you had gone, you had taken this, the flow of this was this way. So if you go this way, negative, a lot of ways you could look at it. If you're going to call this the flow from here to here, the way you would do this, you'd go against this gain potential. That's 8. Subtract, that's that. 8 minus 4 is 4. That's 4. From 4 down to here would have to be 0. So A would have to be at the higher potential. Very awkward setup in that regard. I'm almost wondering how that would work out if we just, this is kind of like off script, you guys, but if I put something there and then try to actually look at it, perhaps that would be something a little more reasonable to do with that. So part of me wants to say, well, that's the answer. I mean, the answer is it's a potential difference is 4 volts, and A has the higher potential. Let me just go off script a little bit on this one, which may or may not be worthwhile. Let's kind of see. Let's look at it. If I looked at it here, if I connected these, if I connected them, what's going on? That's a good question. A good way to know what has higher potential is the flow should be this way. So we could say a lot of stuff, guys. We could say that there is current flowing say a lot there. They put a 10 right there. I'm not sure the 10 would matter a lot. Just for the sake of argument. Let's look at this. Let's say this went this way and then broke here and then broke this way here. Perhaps that answers, maybe this, I'm looking for a more intuitive look at this, guys. Let's call that I. Let's call that I1. Let's call this I2. Let's call this I3. If they were indeed connected, it may not, so this may not be something that we're looking at here. We could say a lot. I mean, if they were connected, there's a conclusion we can draw, but it may not be what they're asking for as far as what's happening in that regard. So let me see what I can say. Plus 12 minus 2I1 minus 4I2 equals 0. True. This would be negative. Go this way. This would be negative 4I2. Forgive me, that'd be positive 4I2. Positive 4I2 minus 4. Minus 10I3. If it was, I mean, now it's not. They're telling us it's not, so we're probably not going to go there. But let's see here. That'd be plus 4I2 minus 4. Plus 4I2 minus 4 minus 4I3 equals 0. I'd say that I1 equals I2. I1 equals I2 plus I3. Yeah, I mean, something along these lines, I guess you could say. My guess is that the I3 is the right direction. If that's higher potential, if A is higher potential than B, I think I picked the right direction for that, and we can actually find that out. And again, this is completely off script, you guys. So let me try to see what I could say here. You got 12 right here, and you got the 2I. Let me substitute. For I1, I2 plus I3, so that's negative 2 negative 2 times this is negative 2I2 plus negative 2I2 plus negative 2I3 plus negative 4I2. Yeah, true. Negative 4I2 and negative 2I2 is negative 6I2. The other one, negative 4, negative, I'm sorry, negative 4, that's 4I2. 4I2 plus 10I3. See, they didn't have the 10I3 in there for some reason, which is kind of interesting. And that equals 0. Yeah, it's 2 equations and 2 unknowns. Multiply by 5 all the way across on this one. Five, right? Multiply by 5. Multiply by 5 all the way across. 5 all the way across, you get negative 10I3. Take these two and add them together. Okay, guys, it's completely off script. If we got to ignore it, we'll ignore it, I guess. A little different story. 28, I mean, it would have been really nice. I2 is about 2. And I3 what would be that answer? I mean, I3, add a positive 2I3 on each side and divide by 2. I3 would be $12 plus a negative 6 times something less than 2, times something more than 2, actually. Yeah, it's interesting. If you actually were to connect it with a wire, it's a different dynamic. The flow of I3 is going to be 2 points according to the math, unless I made a careless mistake here. This is 2 and 2. This is 2 and 2/13. This is going to be a negative number, which means that this is flowing the other direction if they're connected. It's a different dynamic. They didn't propose it. They didn't propose them to be connected. So the way that they showed us how to solve it is what we had actually done. So something to think about. When it's connected, it is a different dynamic. Okay. Last one that I wanted to look at, guys, is number 59. Number 59, a voltage delta V is applied to a series configuration of N resistors. There's a voltage delta V. A voltage delta V is applied to a series configuration of N resistors. So they're in series. Each of the resistors in series is of resistance R. The circuit components are connected in a parallel configuration, and voltage delta V is again applied. Show that the power consumed by the series configuration is 1 over N squared times the power consumed by the parallel configuration. Okay, this is easier done than said, you guys. This should be a little smoother than this particular problem was. Yeah, it's a little odd how this all plays out. Yeah, it's a different dynamic if they're connected, guys. But it's a very ambiguous question, the way 57 was spoken of, I guess you could say. So I'll try not to throw that your way on any kind of exam, but something to look at. I mean, you saw the circuit analysis that we did. I was anticipating. It turns out that the I3 is going in a different direction that we wrote, according to the math that we did, unless there was, some sort of arithmetic error, and hopefully there was not. Okay, so for this right here, they say something, and so let's follow what they say. They're basically telling you there's a series configuration and there's a parallel configuration. You can make a long story short, you can put N resistors. You could put N identical resistors, identical in the sense that each resistor has resistance R. You can put each resistor has resistance R, so there's N resistors, each resistor has resistance R. You could put the resistors in series and find out certain things about what happens in a circuit that has all these N resistors all in series with one another. And you can also find out what would happen if you had all N of these resistors not in series, like the first configuration, the first scenario, all the resistors are in series. Okay. In a second scenario, those same exact resistors, identical resistors, are all in parallel this time. They're asking, show that the power consumed by the series configuration is 1 over N squared times the power consumed by the parallel configuration. The parallel configuration consumes more power. They want you to show that. So, okay. See, perhaps it's a lot easier than maybe the question makes it sound like. We know, once again, power equals IV or I delta V, right? Power equals IV, power equals I squared R. Power equals V squared over R. They're all valid. Tell you what. Okay, so you call it IV or I delta V. Let's use delta V. They've been using delta V. Tell you what, how much power is consumed by all N of these, how much power is used or consumed by all N of these resistors if they're in series? If the N resistors are in series, you add up the resistances. You add up the resistances of all the resistors. You just add them up. You add up the the resistance of each resistor. Resistor R1 plus resistor R2 plus resistor R3. So the power consumed, and like I said, we wrote it like this. I don't want to get too, I don't want to irritate you too much, guys, on this, but you got, so they're using delta V, and like I said, there's more merit to what than using just V. V is just a little easier shorthand, I guess you could say. It's a little more convenient. You can write it like that too. Okay, you've seen that. What are we talking about? Well, what we're talking about is the power is equal to the potential difference. So they're set up. Let's be very careful how they ask this, guys. A voltage delta V is applied. A voltage delta V is applied to a series configuration of N resistors, each of resistance R. The circuit components are reconnected in a parallel configuration, and voltage delta V is again applied. Show that the power consumed by the series configuration is 1 over N squared times the power consumed by the parallel configuration. So much can be said here, guys, how this all plays out. Get the equivalent resistance and go for it. See, you got to remember, there is a potential drop in a series. Every time you go through a resistor, the potential has dropped. Okay, we can take care of that. Let's just get an equivalent resistor by adding all the resistors together. Add the resistances of all the resistors all together. If they're in series, just straight out add them together, and you get the equivalent of one big resistor. Well, if you add N resistors together, if you add the resistances of N resistors, each one having the same resistance R, it's just N times R. That's the resistance. That's the resistance of the total resistance over delta V squared. You got that one. The other one's in parallel. Well, let's maybe first things first. Huh? We'll get to the parallel in a second. Let's talk about this. Well, what the heck does this mean anyway? For series, that means 1 over N times delta V squared over R. That's for series. Sorry guys, I'm running out of chalk here. All right, that's series. Let's compare it to the parallel. Why don't we go? You could write this a whole bunch of ways too. The way I wrote it was okay in my notes. I perhaps could have done it differently and it would have been faster, but I don't know if it's as intuitive. May I ask you a question? What's the equivalent resistance of N identical resistors? Identical in the sense, size, shape, resistance, identical resistance for each resistor. N identical resistors, each one of them put by themselves in parallel with all the other ones. They're all in parallel. They're all parallel to one another. Nothing in series whatsoever in this arrangement. Well, didn't we say that 1 over R equals 1 over R1 1 over r, for parallel, 1 over r equals 1 over r1 plus 1 over r2 plus 1 over r3 plus dot, 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 plus 1 over r sub n. That's 1 over r. True. Well, how about 1 over 1 over r? The reciprocal of 1 over r, you want to divide by r. I'm sorry I'm doing it like this, guys. You want to just take this quantity, delta V squared, divide it by r. Well, what's r? Well, r is the reciprocal of 1 over r. Yeah, but what's 1 over r? 1 over r is 1 over r1 plus 1 over r2 plus 1 over dot, dot, dot. You get the picture. N of them. What does that mean? See, the big thing, guys, one over r equals 1 over r1 plus 1 over r2 plus dot, dot, dot plus 1 over r sub n. True. So r is equal to 1 over r is equal to 1 over r. What is 1 over r? It's 1 over r1 plus 1 over r2 plus dot, dot, dot plus 1 over r sub n. True. And that's why I did it right here. That's why we did that. Now, what is this? Well, r1 is equal to r. r2 is equal to r. Rn is equal to r. They're all r's. There's n of these 1 over r's right here, guys. Guys, I'm running out of good chalk here. Hold on. Sounds good to me. What are we at? One is 1. 1 over r plus 1 over r plus dot, 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 dot plus 1 over r, because r sub 1, r sub 2, r sub 3, dot, 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 r sub n, they're all equal to r. So n of these, there's n of these 1 over r's. N times there's n of them. What do we got? Power equals delta V squared, 1 over. N times 1 over r is n over r. One over n over r is r over n on the bottom. This divided by this is n delta V squared over r. This is for series. This is for parallel, rather. Parallel. Parallel. Series. Which one's a bigger number? Well, according to this situation, for the given potential difference, this is the power dissipated when all n resistors, each one of resistance R, this is the power that is dissipated in that scenario when it's a series configuration. When it's a parallel configuration, this is the power dissipated. N is bigger than 1 over n. Power associated with parallel compared to power associated with series. Parallel so this is parallel, that's series. Yeah, true, true. N, it just comes. These cancel. 1, 1, they cancel. There's just a 1 here, there's just a 1 here, a 1 here. They cancel. 1, 1, okay. N divided by 1 over n is n squared. When they're in parallel, compared to when they're in series, n squared times more power is dissipated. N times more power is, n squared rather, I'm sorry, n squared times more power. N squared times more power is consumed. N squared times more power is consumed by the parallel configuration compared to the series configuration. In other words, parallel configuration, n squared times more power than the series configuration. Put another way, the series configuration, as described, the series configuration, this is true, the series configuration consumes 1 over n squared times the power as the parallel configuration. And that's what they were kind of asking us. They're mathematically the same. We're just answering the question in a different way if you answer one way or the other, but you're really answering the same question. The parallel configuration it consumes n squared times the power than the series configuration consumes. What does that mean? What we just said. Parallel configuration consumes n squared times the power that the series configuration consumes, which means that the series configuration consumes 1 over n squared, the amount of power that the parallel configuration consumes. Same thing. And that's somewhat, and again, the notes are here, guys. And I say the way I wrote it, it's there, you see it. Okay, fantastic. Thank you all for your time. Take care.